these are the 4.4 notes on applications of exponential and power functions. And so the first part of the notes, we're just going to recap the ideas of solving. So kind of brings together the last several days of how we're doing solving with exponents and roots and rational exponents. So just kind of recover those ideas and make sure we're feeling good about that. And the second part will be our applications. And so what we're really going to do there is talk about growth and decay models. And they are some of the best uses of our exponential functions when we talk about applications. So let's go ahead and get going with the review stuff. So here's a set of solving questions. Everything's a little bit different here. We've got a root. We've got just a kind of our typical exponent. We've got a rational exponent. And the idea is, how do we eliminate these things so we get down to just plain x for the purpose of solving, because of course solving means solve for x. So when we look at our root on this side, the idea now is, can you guys identify this as being a fourth root without having to do the rewrite? It's best, to save some time. I know the first day we do this, I had you guys rewrite it as x to the 1/4. Then what exponent would you use? But if I just look at it and go, hey, that is a 1/4 exponent. And the way I would eliminate a 1/4 exponent is raise it to the 4th. So hopefully at this point you don't have to do so much rewriting and you can just get right into the solving. And then go to my calculator to finish it off. Now on the other hand, how do I get rid of an exponent of 4? Well, it'd be the opposite of what we did here. I would raise it to the 1/4. We could also say take the 4th root, but I think the idea of sticking with power to power is still best. So 1/4 exponent, and then go ahead and answer your question. So that turns into a 1, so x equals. Now I put in no solution here, and the reason is because it is no solution, but can you guys determine why it's no solution? Why is that you take the 4th root of -16 and you don't get an answer? And the way to reason that out is, how would you get -16, and what does a 4th exponent mean? 4th means a number multiplied by itself 4 times. So what you're really saying is what times itself 4 times would produce -16. Now I think people are thinking 2, but try it, because you have to use the same number each time. So 4 2's does not equal -16, it equals +16. So you might go, well, okay, I'm going to go -2, fine. But 4 -2's also does not equal 16. It equals +16. So this is actually not possible. You can't take any number raised to the 4th or any even exponent and get a negative result. So if you recognize that, you might not even do this at all. You might just go, hey, it's no solution, I can't do that. But if you don't, or for example, let's say you go to your calculator, like none of this hits you. Your calculator is going to give you an error, and hopefully you realize it's not that you did something wrong on your calculator, it's that it's trying to tell you, hey, this can't happen. Okay, so that may pop up once in a while, a little curveball there. Otherwise, doing this kind of problem, like these, we had our x's pretty much by themselves right away, so it was kind of just get going with get rid of the exponent or the root. But here there's some cleanup to do, like this stuff has to be taken off, that 5's got to be taken off, that 6 has got to be taken off. So we got to go through a little bit of algebra. So this is dividing both sides by 5. Then subtract your 6, and then get rid of your 3/2 by raising it to its reciprocal exponent, which would be 2/3. So remember here the idea is power to power, that's going to give me a 1. And then, either you're going calculator, or I mentioned this to you guys in the last set of notes, can you do this part in your head? Like where you sort of break it up. And I think even this is overblown a little bit. I might just go, hey, it's the 3rd root. Remember I told you guys that this really means 2 things. It means a 3rd root and then squared. So a 3rd root of 27 is 3, 3 squared is 9. Or you could reason it out this way. Again, if this thing is not working for you guys, like the idea of doing it in your head or realizing even that you can do it in your head, calculator is fine. So you can always rely on that calculator. Okay, a little bit more of just working with exponents. So this is kind of back to the rules of exponents, where you've got exponent on the outside that needs to be distributed. So the first thing to do is, apply it to both pieces. Here it's a power to power, so that's multiplication. Here, this can be done without a calculator if you can recognize that. If you don't, it's fine. You can do it on the calculator, you'll be fine. But remember the pieces here, it's a 3rd root and to the 5th. So a 3rd root of 8 is actually 2, and 2 to the 5th is 32. Now over here on this side, I did 5 times 9 is 45 thirds, and then 45 divided by 3 is 15. Final answer. So some of these ideas of how you can shortcut things a little bit without a calculator, maybe it'll speed it up, maybe it won't, but I think it's good to practice those ideas. Again, a 3/4 needs to be distributed to both pieces, so get it distributed to both. Turns out you can do this without a calculator if you know your, now here's the catch, right? You got to know your 3rd roots, you got to know your 4th roots, so if you don't know some of those, that would be harder without a calculator. And then 12 times 3/4, 36/4. So if I decide to go without a calculator, remember this has 2 pieces, it's a 4th root to the 3rd. The 4th root of 81 is 3, 3 to the 3rd is 27, and then here we're just simplifying that, bring it with. So as you're doing these problems, you kind of have to decide to yourself which way you want to go, calculator, no calculator, but just be sure that you absolutely distribute that exponent to both parts and not just to one or the other when you do that work. Okay, let's get into our application, which is the growth and decay models. It's a pretty simple looking equation. Looks a lot like our explicit format, our explicit rule, if we're talking about it as a sequence rule. But your A number will be your starter value, so it's like your use of 0. So going back to that same idea, right? What's your initial value? And we're talking about objects typically here, so a dollar amount, what it's worth. R, again, is your value that is either your value remaining or your value gained expressed as a decimal. So that'll depend on the problem. If it's a growth or a decay idea, we'll think about which one is which. And then how you determine growth rate or decay rate. And we've been doing this already in other chapters. We just never talked about it as this sort of these little mini equations, and I'll explain that to you guys in a minute. But it's really the explicit rule. And then of course we're talking about objects either gaining or losing value. Everything happens over time, so that T up there is referring to time, usually in years. It wouldn't have to be, but that's pretty typical to go in years. So let's look at a problem. So the first thing to do is here are a bunch of functions, and basically we want to just identify which type we have, a growth or decay. So the first one's investment. We did a bunch of investment stuff in other chapters. The second one's a temperature of a cup of coffee as it sits on your kitchen room table, as your kitchen counter, excuse me. And then the value of a car you purchase over time, and we know that cars typically lose value over time. Again, really easy to know. We already discussed how we know if it's a growth or a decay in previous sections, because you look at our R and just, is it bigger than 1 or not, right? Like our base also. So that being bigger than 1, that's definitely a growth. When I go to figure out what the growth rate is, it's really how much is it over 1. So it's over 1 by 15%, sorry, by 1.5%. So I got a 1.5% growth rate. This is clearly a decay because the number is less than 0. Sorry, the number is less than 1. Between 0 and 1. So sorry, recap one more time. That number being between 0 and 1 makes it a decay. But what we're really saying here is it's maintaining 78% of its temperature in this case. So how much is it losing? Well, it's losing 22% then. So the decay rate is 22%. That's the loss. In this case, maybe over time in minutes. And then the value of your car. Well, again, it's depreciating because that number is between 0 and 1. But what this actually says is your car has 85% of its value. What is it losing? What's the decay rate? It's losing 15%. So we've done this in past chapters when we looked at explicit and recursive rules, doing those kind of problems, or even we did the investment stuff, like the idea of how does this number match up with what's happening in the problem. So you got to keep that straight as you set it up yourself. You got to write your own function, which we're going to do next. What are you plugging in? How are you going to write this correctly? Based on losing or gaining value. Okay, so here's a model of a newspaper company. They're experiencing a reduction in circulation. The newspaper's audience is going to the internet more and more, so which is true today. That not a lot of people still read a newspaper, right? You go to your favorite news provider online and read your news there. So they create a model that shows how they're losing subscriptions based on a yearly model. And they started collecting their data in 2015, so that's going to be your starter year. Number one is it a growth or a decay? Well, when you read the word reduction, that should scream decay, right? We're losing subscribers, so values going, or number of subscriptions are going down. What can you tell from the model about the starting number of subscriptions? Like in 2015, how many people were subscribing? The idea is in this year when they started collecting data, that was time equals 0. So time hadn't passed yet. We're going to start getting the information. Then as we go to 16, 17, 2020, time is passing. Now we can start about years in the model. So if time is 0 and you were to plug that into the equation, so plug in for t, remember what 0 does as an exponent. 0 turns this into 1 because anything to the 0 power is 1. So if 0.89 to the 0 is 1 times 20,000, then my a out front, which we talked about this in the past, is like a y-intercept if we were graphing, right? Or my starter value as a recursive rule, it's my starter number of subscriptions. So 20,000 people had subscribed in 2015, and then time started to pass, and we started to lose subscribers. Okay, then model it with what happens in 5 years. Well, okay, so then what's the S of 5? This is all calculation on your calculator. You can see the subscriptions went down. Also remember that as a decimal goes, when you're talking about your subscribers, as a number, they're people, right? So that number has to disappear, and a whole number, we always round down to the whole number.